PMEL, we worked with Rudy Preisendorfer there, right? I'm pretty sure. And then he was at UW for a little bit, University of Washington for a little bit, SRI for a little bit, ONR for a little bit. And in '97, it's hard to believe it's been that long. He settled into Sequoia and is now Vice President of Science at Sequoia and a senior researcher or something like that.
Yeah, all it means is I can sign paychecks.
Yeah, so there you are. The thing that Curt, for those not in the field exactly know, probably his claim to fame, I think, is that he developed the Hydrolite program, which has allowed more people than probably should to be able to radiate transfer technologies. So he's brought in the interest of people in biology and stuff in radiation transfer. So anyway, there you are.
Okay, well, thank you. It's truly a great honor to be here. I consider myself unworthy even to have my shadow follow in Howard's footprints. So to be invited here is a great honor. And for my talk, I wanted to find something that would be of amusement to Howard and maybe educational for the rest of you who don't live in the world of radiation transfer theory. So I put together a little talk here with some stuff I've been doing over the last year. I have this collection of topics I've been collecting for 30 years. It says, someday you should look into whatever, and I'm sort of starting to work through that list now, and this is one of the things that came up on that list, was looking at doing a better job of predicting light reflection and transmission by ocean surfaces. So to do that, you know, this is going to be Monte Carlo modeling, and we really need to do three things. We need to model the sea surface correctly, which means I need to simulate both the wave elevations and the wave slopes, and do that in a proper fashion. I'm talking about light, so I really need to include polarization. And of course, sometimes a light ray comes in, hits a wave facet here, bounces over here, and hits another one. So I need to include multiple scattering. And I'll show you in the course of my talk how I do all of that. So, somebody mentioned Cox-Monk surfaces a minute ago. I'm going to comment about those very briefly. They're what is used by almost everybody in the field, and they get part of the sea surface correct, but not the other part. But mostly I'm going to talk about how to use what are called wave variance spectra and Fourier transforms to model the sea surface and fully resolve both the elevation and the slope statistics of the sea surface. I'll spend a good bit of time on a couple of those equations because that's really the core of what I'm doing here. I won't say much about Monte Carlo ray tracing, one view graph, let it go at that. And I'll show you a few examples then of doing some of these calculations, and I'll try to get you out the door knowing the answers to a few questions here about things like how good are these Cox-Monk surfaces versus a real sea surface, and how important is it that you include polarization, how important is it that you include multiple scattering, and so on. Now, a bit of personal history to start off. I first met Howard at the 1986 Ocean Optics Conference. At the time, I was sort of a half postdoc, half computer programmer for this fellow Rudy Preisendorfer, and we had put together some simulations of the sea surface to look at reflectance and glitter patterns of sea surfaces. So I spotted this Ocean Optics Conference, and my background is not optics, not oceanography. I've never had an oceanography class, I've never had an optics class. I'm totally unqualified to do anything in this field, but I spotted this conference and I told Rudy I wanted to go to it. It looked interesting. And so he sent me off to, I think it was Orlando, somewhere in Florida, to give a talk on this work we had been doing on simulating reflectances by sea surfaces. And that was 1986. At that time, we were using Cox-Monk sea surfaces. It was unpolarized ray tracing, although Rudy and I had worked out a technique for including all the multiple scattering. And in those days, the Ocean Optics Conference, as I recall, was maybe 30 or 35 people, which was Howard, George, Ray Jerry Smith, Jules Jaffe, Ron Sanfeld, all those guys. And that was, yeah, it was very informal. Some people would give 2 or 3 talks. Today, you go to the Oceanoptics Conference, it's 400 people. And an amazing growth in the field. But anyway, this is sort of how I got started in the field, was calculating surface reflectances. And that's how I'm almost finishing my career now, is still calculating surface reflectances, but doing it a little better. And Rudy and I were at this NOAA Pacific Grade Environmental Lab, and I see the pen has died here, but anyway, here we go. At the time, we had access to a NOAA CDC 6600 supercomputer for which we could do 2,000 surface realizations. And this is all punch cards. You punch out the cards, you put them in, and the next day, if you were lucky, you would get back the answer in a big stack of paper. Now, it cost 11 cents a second for the computer time. And I remember, and Rudy had to bring that money in on a proposal, still fundamental to many. Good job of capturing the slope statistics of the sea surface. And it's a real compliment to Cox and Monk that a paper that was published in 1954 is still fundamental to many people's calculations in optical oceanography. They really got it pretty close to right. When you want to generate a surface using these equations, what you do is take a patch of ocean, divide it up into a lot of little triangles, and then at the vertex of each triangle you can use these statistics or these equations, and you can draw random numbers, and you can generate random surface elevations such that the slopes of the little wave facets will then give you the variances that they're. Fully resolved sea surfaces using Fourier transforms, polarized ray tracing. I can now do 100,000 surface realizations in far less time than the 2,000 cost me before. And of course, it's maybe 10 cents or something like that for the amortized cost of this laptop. Okay, so that's what it's all about. Just to comment on these Cox-Monk surfaces. The idea was that Cox and Monk flew over the ocean in an airplane, and they took a picture of the glitter pattern of the oceans. They knew where the sun was, they knew where they were looking, so they could figure out how the wave facet had to be tilted to reflect the sun and create the glitter pattern. And they have this classic paper from 1954. And out of that work, they came out with what's called the Cox-Monk wind speed wave slope statistics that give you the variance of the along wind, the crosswind, and the total wave slope as a function of the wind speed W. Very simple little equations, but they do an amazingly good job of capturing the slope statistics of the sea surface. And it's a real compliment to Cox and Monk that a paper that was published in 1954 is still fundamental to many people's calculations in optical oceanography. They really got it pretty close to right. When you want to generate a surface using these equations, what you do is take a patch of ocean, divide it up into a lot of little triangles, and then at the vertex of each triangle you can use these statistics or these equations, and you can draw random numbers, and you can generate random surface elevations such that the slopes of the little wave facets will then give you the variances that their equations said you should get. When you generate a surface like that, you get something that looks like this. It just doesn't look right. The reason is it doesn't have the elevation statistics. So if you go in and you take all these little slope statistics, see if you can find me a pointer or something. This reproduces the right slope statistics, but the elevation is just a little crinkly surface. So it doesn't look quite right. But the reason it works halfway well is that the first order, it's the slope of the surface that matters when a ray hits the surface and bounces off. Well, George saves the day once again. All right. Look at that, it's even green. Okay, so anyway, this is the kind of surfaces that I've been using for 30 years. It's the kind of surface not quite right there. So what we want to do is generate a sea surface that has both the large gravity waves all the way down to the smallest capillary waves. A little review, what we're going to do is the following. Think if you take a patch of the ocean surface that I call size Lx by Ly, so that might be 100 meters on a side, and you're going to sample that surface at some Nx times Ny number of points, so that might be 1,000 points in each direction. You do that, you end up now with a sample of the sea surface at some xr, ys points here, which I'll just call z sub rs, where r runs from 0 to nx minus 1 and s runs from 0 to ny minus 1, depending on how many points you have. Okay, that's a random sample of the sea surface. Boom, got it. If you take this array of numbers and you feed it into what's called the forward discrete Fourier transform, which is defined by this equation, you take your numbers, you plug them in here, you do this by calling a subroutine, and we're going to let our number of points nx and ny be a power of 2 so that we can use what's called the fast Fourier transform. Well, you just plug in your numbers, call the subroutine, it comes back and it gives you an array of complex numbers which are called the amplitudes. And there's the same number of amplitudes as there are points that you put in here. Two things to be said. The subroutine will give you back this array of numbers, and it'll say, and here's the array of spatial frequencies that correspond to these numbers. Now, notice the spatial frequencies, first of all, they're units of radians per meter, and some of them are negative. They go from minus n over 2 plus 1 up to minus 1 to 0 to 1, n over 2 minus 1, and then there's finding one more, n over 2 times 2 pi over the size there. Well, that's kind of weird, so what's a negative frequency mean? Well, all that's going on here, George got one. There we go.
I will leave my office.
I can do a red one in one hand and a green one in the other. That'll keep you awake. Okay, so basically what it's done is take a snapshot of the sea surface. There's no time information there. You feed it into the Fourier routine, and it says, I don't know anything about the direction the wave's going. I can see the surface elevation, but is it going this way or that way? I can't tell. There's no time information. So if you pick that direction and call it plus k, and say a wave going in that direction is a positive frequency, then the wave going in that direction is the negative frequency. That's all it amounts to. And it will put equal amplitudes on each direction. So you could think of it, it's like a standing wave. You've got two waves going in each direction, and it can't tell the difference. So anyway, that's just a little quirk that if you haven't played with Fourier transforms before, you start wondering about what's going on with negative frequencies. It's nothing except the math telling you, I don't have enough information to tell you what direction the wave is propagating. The second thing is you're putting in a certain number of elevations, and you're getting back the same number of complex numbers. Well, the complex numbers got two elements, a real and an imaginary part. But these amplitudes are Hermitian, and that means that the complex conjugate of the amplitude at the minus k is equal to the amplitude at the plus k. So that means there's not, the real and imaginary parts are not all independent. So the amplitudes have the same amount of information as the original surface measurements. They're just in a different form. Now, I need to go in the other direction. I don't have the sea surface elevation. That's what I'm trying to generate. So what I'm going to have to do some way is conjure up some amplitudes so that I can take them and go in the inverse direction and come up with a sea surface. Well, how you do that is with what's called wave elevation variance spectral densities. Well, fancy word, but what it amounts to is these functions, and I can write it either as k's in the x and y directions or a k magnitude at an angle. They are functions such that if you integrate this thing over all frequencies, and notice both negative and positive frequencies, this by definition gives you back the variance of the sea surface, so z squared. And the mean elevation of the sea surface will be 0. Now, these things are usually sort of partitioned like this. There's what's called the omnidirectional variance spectrum, S here. That tells you how much variance there is per unit frequency interval at a given frequency without regard to what direction the wave is going. And there's a spreading function that tells you how the angular distribution of the waves is actually propagated. And so anyway, if you go to the literature, you read a paper on sea surface wave variance spectra, and they're often called energy spectra or power spectra because the wave energy is proportional to the amplitude squared. So people call these energy spectra. Well, they're really variance spectra, and if you want to get energy, you have to multiply by some additional factors out here to turn the meters squared into energy units. But anyway, so here from a paper by Haile et al. 1997, one of my favorite spectra. Here's this S of K function. Notice it's got units of meters squared per frequency or radians per meter interval. They drop off very sharply at low frequencies. There's a peak here. This is the long gravity waves that have the most elevation in them, so the most variance in elevation or the most energy. They drop off rapidly with increasing wave number. The dotted line is the boundary between gravity waves on the left and capillary waves to the right. And then out here there's a viscous drop off with the very short capillary waves. And so that's what one of these things looks like. For low frequency waves, they're strongly weighted, so the waves are heading downwind, not much crosswind. At higher frequencies, you have waves kind of heading off in all directions. And in this case, this thing is symmetric for plus and minus k values because that's what comes out of the Fourier transform. So anyway, what we're going to do is we're going to go to the literature, we're going to find our favorite wave elevation variance spectrum, and some way turn that into amplitudes that I can plug in to the Fourier equations. So here's the first subtlety. You go to the computer-generated imagery literature where people use this stuff to generate sea surfaces for movies and video games. And they have an equation that looks sort of like this. They've taken their elevation variance spectrum, and remember this thing is proportional to the variance, so that's surface elevation squared. So they take the square root, so you get to an amplitude that's in meters. So that's where the square root comes from. And then they use some random numbers, which are basically going to make the phase of each wave random, and they'll come up with an amplitude. Crucial thing here, I have a stack of these papers about this thick on my desk, and every single one of them does the math incorrectly. And what they miss is the following. Back up. The Fourier transform comes back and gives you positive and negative frequencies. The physical oceanographer types usually say, I don't care what direction the wave's going, I just want to know how much variance or how much energy is in the wave at a given frequency. So they fold the negative frequencies over on top of the positive frequencies, and they add them together, and they plot what is called a one-sided or a folded spectrum. So I'm only plotting positive K frequencies. But the real spectrum is half of this magnitude, but it's symmetric in the negative. So you have to take the numbers out of the literature, whoops, and divide by 2. The next thing is if this function is a continuous density function, you're working with the discrete transforms and discrete surfaces, so you need to multiply the density by the bandwidths of your actual discrete sampling. That turns the density into a discrete point function. And so you do that, and that basically turns your one-sided or folded spectrum back into a two-sided, because we're going to now have both positive and negative K values. And then you pick some normal 0, 1 random numbers, and you come up with this z hat 0 here. Well, this is nice because if you take the expectation of this Z0 hat squared, you'll eventually then end up with the wave spectrum you started with. Well, that's half of it. But the catch is this function is not Hermitian. So if I plug these things into my inverse Fourier transform, I'm going to come back with a complex C-surface. I need to have a real C-surface. So what I do is I just take this thing and I take its Hermitian conjugate, and I'm going to throw in time dependence here just to make it completely general. And now I have a function for the amplitudes that is based on my chosen wave spectrum, and this thing is now Hermitian, and if you take the expectation of this thing squared, you'll end up with the positive frequencies plus the negative, 1/2 that sum, and if these are equal, which they are for my problem here, then you end up with what you started with up here. So I read through the literature, I pulled out these equations, I programmed them up. The first thing I did was generate a C-surface, and then I went back, and it didn't get back to where I started. So I worked and I worked and I worked on this, and I just couldn't figure it out, so I re-derived all these equations from scratch, and I come up with a factor of 2 there, and I come up with another factor of 2 here. And so I tracked down the guy named Jerry Tessendorf, a friend of mine, who sort of pioneered the use of this equation. And he's got a very influential set of notes where he shows the movie industry how to use this equation to generate C-surfaces. So I called him up and I said, Jerry, I'm just lost. I've got 15 papers here. They all use your equation, and it looks to me like your equation is missing a factor of 2 here, it's missing a factor of 2 here. Because without these, when you go through the process and you square it, you'll end up off by a factor of 4 on energy conservation. And he said, and then a lot of the papers don't include this term here either. They just pull a function out of the literature, plug in numbers, and generate a surface. So I said, Jerry, I don't know, I'm totally lost. Now, Jerry got an Academy Award for technical contributions to the movie industry for showing them how to generate C-surfaces with this equation here. And his first movie was Waterworld. He did Titanic. He's done about 15 more now. And, oh, Curt, yeah, your equations are correct. Mine aren't. But you're so clueless. Hollywood doesn't care about conservation. So you can imagine how shocked I was to find out that Hollywood is making movies where the physics is not correct. What can I say? Well, anyway, so at least I got that right. Tessendorf understands all this stuff. And he said, I'll generate a sea surface that's maybe 100 meters square. And then they have these things called graphics artists. And they'll say, well, the ocean doesn't look rough enough. So they'll squash it down to 10 meters square. And then the ocean looks rougher. So their argument is factors of 2 and such don't matter because we're going to adjust the sea surface for artistic purposes. Well, I'm going to do real calculations here. So I need to get it right. Okay, the second subtlety is here's my spectrum here, the blue line, and if I integrate that from some really small number out to some really big one, I'm basically then computing the total variance of the sea surface. Well, I'm only going to sample this from, say, this point to this point, so there's a fundamental frequency that is determined by the size of the spatial region, so it's 10 meters square, 100 meters square, whatever. That determines my fundamental frequency, and how many points I sample is 512, 1024, 2048. That determines how far out here I go, and the last point is what's called the Nyquist frequency. Now, for the elevations, if I integrate the blue curve from here to here, I capture 98% of the total interval. That's good enough for movie making, because when you look at waves, visually what you see is how big the waves are in amplitude. You don't see the slopes of the things. On the other hand, what's important for optics is the slope of the surface. Now, the slope spectrum, it turns out, is k squared, frequency squared, times the amplitude spectrum. So that drops off much slower here. And if I integrate then the slope spectrum from this point to this one, corresponding to those, in this particular example, I only capture 43% of the slope variance. So I'm making a surface that is not rough enough. And that means the surface isn't rough enough, it's going to reflect too much light. That's a big deal for me in optics. So I have to figure out some way to realize that I'm not sampling all of this variance out here, and I have to some way account for that. Well, what I do there is I, first of all, integrate the whole slope spectrum. I find out how much I'm missing out here, and then I sort of fold that over, and I increase the spectrum. Here's the green line. I cook up a little function here that says take the true spectrum, which is the blue line, and add some extra in at the higher frequencies and create this adjusted spectrum, so that when I integrate the adjusted spectrum, the green curve, from here to here, I get essentially 100% of the slope variance without having to actually go out here and sample. So I can do relatively few samples, but I've made the energy variance a little bit too great. And so I've captured all of the slope variance, and I've now captured a little bit too much elevation variance. Here I had 98%, 1.02 or 102%. So I've added a little bit too much slope, or too much elevation, but I've captured the slopes, and that's what's important. Okay, so I do that. I take my favorite spectrum, I tweak it a little bit, and this tweak depends on the wind speed and the size of the region and the number of points, but it's pretty straightforward to determine. Anyway, I take the tweak thing, I plug it in to the, create a spectrum here, a wave number elevation variance spectrum. I can take that, I can plug it into the Tessendorf formula with the right factors. I can generate these amplitudes, which are now Hermitian, and then I plug these guys into the inverse discrete Fourier transform, and I come back with a random realization of the sea surface that satisfies, to a very good approximation, both the elevation and the slope statistics of the real sea surface that would be described by whatever spectrum I chose. Okay, so that's the crucial stuff. Here's just a picture of the sea surface. Here's 100 meters by 100 meters, and I did 512 points in each direction. Wind speed of 10 meters per second. Here's just a snapshot of that sea surface. And this guy passes every test I can think of for what is the significant wave height, the mean square slope total, x direction, y direction, and how do these numbers compare with Cox-Monk? Well, 0.053 versus 0.54, 0.32 versus 0.32, etc. So this guy is reproducing the Cox-Monk slope statistics, but it also has the elevation statistics. All right, now I'm going to trace rays with this thing. I create my surface, I shoot photons down, I bounce them around, I see where they go, and I total all that up. I'm going to skip this because I'm running low on time. What I do on the FFT grid, that is a rectangular grid, and when I trace rays, it's a lot easier to have little triangular wave facets, because then the math amounts to finding the intersection of a straight line and a plane, the plane being determined by the three vertices of each little triangle. So it simplifies my math if I take the rectangular grid that's shown in blue here, and I map it to a grid of triangles that will look something like this, and then I'll do my ray tracing on the triangles. Okay, enough said. The old ray tracing code that was developed in 1986 that geometrically says, here's where the rays go and how they bounce around, that still works. I just have to add polarization to those rays. Well, it's easier said than done. You have to, resolve these incident Stokes vectors in an incident meridian plane, and then before you reflect them off of a little triangular wave facet, you have to transform the Stokes vectors into a local coordinate system for that facet that's determined by the normal to the facet and the incident direction and on and on and on. And George and Howard will appreciate that, what a mess that is to figure out all of these angles. And of course, it's going to maybe bounce off of this facet, go over here and hit another one, so you have to transform from this normal and parallel and perpendicular coordinate system for this facet to the one for this one, and then finally this thing may bounce off and leave your computational region, and you now resolve the Stokes vectors into a final meridian grid. And it's a nasty business, but it is just multiplying matrices once you get them all correct. Here's just a couple of examples of some reflectance and transmissions doing all of this. So the simplest possible thing would be to have an unpolarized sun in a black sky. So that's what I have here. So the sun is at 50 degrees. It's unpolarized. There's my Stokes vector, 1000, unpolarized, Fourier transform surface, 10 meters per second, etc. So looking at this when the sun's kind of around the backside, and I'm up here looking down at the ocean, looking at the glitter pattern. So you see the strongest reflected light here is this yellow color, and then it gets darker out here because fewer rays are reflected out to the side, and then rays that got a negligible amount of energy, I didn't bother to color in. So that kind of looks like a glitter pattern. Now, here's one where I'm looking at horizontal versus vertical polarization. And the blue is horizontal, the red is vertical. Notice in this region here, it's very strongly horizontally polarized. Well, that's angles close to the Brewster angle where the incident light is horizontally polarized upon reflection. Okay, so that looks pretty good. I got that right. Here's the plus and minus 45 degree linear polarizations, and they're either plus or minus, and that is determined by the ray comes in. If the facet's tilted this way, it reflects it off that way. The facet's tilted this way, it reflects it that way, and so you get a plus or minus symmetry there. And there's absolutely zero circular polarization in reflected energy. So I do all this kind of stuff as far as I can tell. I have it working correctly. A question here of how many surfaces do I need to generate? How many points, if I pick, say, a 100-meter square patch of the ocean, do I need 512 points, or 1024, or 2048, or how many values do I need there? And I've done a lot of simulations. So if we just plot the reflected light down the middle here, so this is sort of looking through the middle of the glitter pattern. If you generate the surface with 512 points, well, I get the green curve here. If I used 1024 points, I get these red curves, a little different. If I use 2048 points, it's within a couple of percent of the red curves. And there's actually 3 red curves. There's a solid, a dotted, and a dashed line. Those are simulations for 3 different random numbers. So then if you do 4096 points, they're just indistinguishable from these curves. So what you learn from that is 512 computer time. And if I don't do that little scaling with my little fudge factor, so I'm not resolving the unsampled slope variance, then here's the reflectance. Notice I commented if I don't sample the slope variance entirely, the surface is going to be a little too smooth, which will make the reflectance a little too big. So here's the unscaled, and then would not be correct, 1024, and then the red here is after I put on my little fudge factor. So I played around with all of that, I think I understand it, and here's, this is looking at the transmitted light in the water, so I'm under the surface now, looking upward towards the light coming through the surface, and there's the sort of glitter pattern that scuba diver would see, and then there's the different polarization states. Once again, no circular. Here now, just as an example, I said, let's have an underwater light in a black ocean, kind of like the sun in a black sky, but let's let it be partially vertically polarized. So here's the glitter pattern. I'm looking up at the surface. I'm seeing the light reflected back down. And now I see some different looking polarization states. And now I'm seeing some vertical polarization, either left or right, circularly polarized. Well, what's going on there? Well, if you think of how do you generate circular polarization in the laboratory, one way is you use total internal reflection in what's called a Fresnel ROM to generate, put in linear, and you can get out circular. That's what you're seeing here. Total internal reflection, whether it's in the laboratory or in the bottom of the side of the sea surface, can turn linear polarization into circular. And lo and behold, I seem to have that right. Okay. And of course, also, this incident angle was 60 degrees. For a level surface, all of that would be internally reflected, but because I have a wavy sea surface, now and then a facet is tilted so that it goes in at less than the critical angle, and that light can leak through into the air, and there's what you see. All right, enough said on that. Let's do a little more realistic light source now. So here's the sky radiance distribution for a single scattering Rayleigh sky. And the sun in this particular picture, the sun's over here at the left, so we're kind of looking at it from the side. So the sun's at the left. Here's the degree of polarization. So sun's here at a 90-degree angle from the sun around the sky. You're seeing the maximum polarization here. And then there's, you know, in this case, it's plus 45 here, and around on the other side would be minus 45. So I take a sky radiance distribution like this, I feed it in, I reflect it off, and now I'm going to get my IQ, and once again, V is 0. I'll get the polarized reflectance, or the polarized, the reflected and transmitted Stokes vectors. Okay, so let's actually do some science with this. And I said, all right, suppose I have an instrument that's going to measure planar radiance, but it's not sensitive to polarization. So I'm just going to put it out there. I'm going to measure EU and ED, and I'm going to compute the irradiance reflectance for unpolarized. But I can either do my simulations with unpolarized ray tracing and Cox-Monk surfaces and predict what the EU and ED and the ratio of R would be, or I could do those calculations using polarized inputs and FFT surfaces and all of that. So I did a bunch of comparisons here. And for example, if I do the FFT surfaces and I look at the differences in what I would predict for irradiance reflectance for polarized versus unpolarized ray tracing. So the solid symbols are polarized, the dashed and the open symbols are unpolarized. There's, you know, orders sort of like 10% differences here, and they depend a little bit on the wind speed, but basically you get a kind of 10% error there if you ignore polarization. Or if I do polarized ray tracing, but I use FFT surfaces versus Cox-Monk surfaces, once again, there's little differences here, but they're sort of order 10%. Or if I compare the FFT surfaces in polarized versus Cox-Monk and unpolarized, that's what's in hydrolite. This is what will be in the next version. The biggest difference at all that I can find is 18%. Once again, most of the differences for given, these are sun angles across here. Most of the differences are of order 10%. I've looked at what if I do calculations with just single scattering, which is still very commonly done in Monte Carlo simulations. People will draw a Cox-Monk little triangle and they'll do one scattering off of it and that's it. They don't allow for multiple scattering from wave facets. Well, if I throw out all the multiply scattered rays, once again, you see differences here that are sort of order 10%. How about the sun's azimuthal angle? I'm going to have a wind speed in this direction, and I'll have different slope statistics along the wind than I do in the crosswind direction. So if the sun is parallel to the wind or the sun is perpendicular to the wind, you're seeing somewhat different roughnesses on the sea surface. Once again, it's kind of this little 10%, not much difference. How about wave age? If you take a very young sea surface versus a mature versus a fully developed sea surface, all of which can be simulated by picking parameters in your wave variance spectral density, well, once again, it's 10%. So I go through all of this stuff and I kind of conclude that for computation of or prediction of irradiance reflectance, which is telling you how much energy is reflected from all directions into all directions, how much is getting into the sea surface, you're off by about 10%, depending on which way you do things here if you don't do the full-blown calculation. For a lot of purposes, that's acceptable. And so, you know, the hyperlight predictions of R there are off by maybe 10%. On the other hand, if you pick a particular input direction, a particular reflected direction, now those differences are going to be greater. So, way back in '99, I had a paper where I published calculations of what are called this radiance reflectance factor, and our distinguished Ken Carter there invented a technique where basically what you do is you want to get the water leaving radiance. So you can look at a spot in the sky, measure that. This is an unpolarized instrument. You look at this spot. You look at the spot down on the ocean that would be specularly reflected into your instrument, and you measure that. And then you put a gray card under this, and you measure that, and that gives you the ED on the surface. But there's a step in that calculation where when you look down here, you're measuring the total light reflected by the ocean, which is all the sun glint and all the sky reflectance, plus the water leaving radiance. And you need to know how much of that surface reflected light to subtract out of what you measured, so that what's left is the water leaving radiance. Well, if the sky were uniform and if the ocean surface were level, that reflectance factor would just be the Fresnel reflectance and life would be good. The problem is skies are not uniform and surfaces are not level. So I computed a bunch of tables here using Cox-Monk surfaces and unpolarized ray tracing, and I looked at these reflectance factors, which is the ratio of the surface reflected light to the skylight. So that's this skylight and this surface reflectance, and just what's the ratio is rho. And I looked at that as a function of viewing directions and wind speed and so forth. And so here, for example, 10 meters per second, and this is a couple of different off-nadir viewing directions and a couple of different azimuthal directions relative to the sun. So if the sun's over here and I'm looking here, that's a 90-degree azimuthal direction. If I look back here, that's 135 degrees. And I conclude that the least variance here is if you look somewhere around 135 degrees and somewhere around 30 or 40 degrees off the nadir. If you look too far around this way, you start picking up sun glint and the factor rises. If you look at this direction, you're looking at your own shadows, so you don't want to do that. So this is a reasonable balance. And there's a table of values that are out on the web that people use that you can say this wind speed, this viewing direction, etc. And they'll look in the table and they'll get the magic rho value that they need. And there's minimum variability out here at this sort of 40-degree or so off-nadir viewing direction. And if you look too far out, rho gets big because of the increasing Fresnel reflectance. If you look too close to the sun, you start picking up sun glare. So my recommendation was use these points here. Now I redo that calculation using the polarized sky input, polarized ray tracing, the FFT surfaces, etc. And notice here, very little variation in the rho value. But here there's much bigger variation in the rho variations for the sky radiance distribution. And those different input sky polarizations then can give you considerably different reflectances, even for just the unreflected or total reflected light. So what you're seeing in the bigger variation on the reflectance here is the variation in the polarized sky conditions, then determining different reflectances here. So another way to plot this is for given as azimuthal directions, is if you plot these things up like this and say, okay, here's the sun's direction, there you're looking at the specular direction. If I look around here, the magic fudge factor here is about 0.045, and this is the full FFT polarization calculation. If I look down here with the old Cox-Monk thing and take the ratio of the new value, it's about 30% or so more, and so on down the line. So these kind of calculations can be off by 20% too small or 30 or 40% too big. They're much more sensitive to viewing direction and sky polarization. Okay, I'm not going to say anything else. Ken's standing up. So just to summarize here, basically I put together the math and the computer codes for generating random sea surfaces that properly simulate both the wave elevation and slope statistics. And I think I've got the math and the computer codes figured out for doing Monte Carlo ray tracing with the full Stokes vector Muir matrix formulation. And this bottom line is that this widely used Cox-Monk model does a reasonable job for some calculations like your radiance reflectance. You may be off by 10%. But it doesn't necessarily do a good job for radiance calculations when you're looking in particular directions if you don't account for polarization. And so I think, enough said there. Doing 100,000 surface generations and tracing rays from every direction for each of those 100,000 surfaces, that's about 7 hours on this laptop. And it's quite easy to do. And there's a big paper on this in press now in Applied Optics, and I've got a couple of copies here if you want to read it on the flight home. So bottom line is there's no more excuse for doing bad surface optics calculations with Cox-Monk surfaces and unpolarized ray tracing and single scattering when it doesn't cost you that much more to do the whole thing correctly. That's it. So Howard, all I can say is thanks for all your contributions to this field. And at that 1986 Ocean Optics meeting, when I gave a talk on this and I showed how we did these multiple scattering calculations and so forth, Howard, after the meeting, said, yeah, Curt, that's the right way to do it. I'm sure you don't remember that, but it was such a big deal to me that Howard Gordon said I was doing things the right way. That I was like, oh, thank God. I have to go home and report to Preisendorfer now that we actually have Howard Gordon's stamp of approval on these rather complicated ray tracing calculations. And so ever since, Howard has been, my hero. And if Howard had said, Curt, you moron, this is worthless, I would have gone off and become a professional mountain climber. Anyway, I'm going to close with one. Whoops. This should be. Here we go. You're seeing here for the first time, ladies and gentlemen, in the history of movie making. Come on. This is a computer-generated image of a sea surface with all the physics correct. I'm awaiting the phone calls from Spielberg to say, Curt, let's do a remake of Titanic and Waterworld and Pirates of the Caribbean and all this, and we'll use your equations and have the physics corrected. And I'll let you know if they give me a call. That's it.